Uh, yes, so I'm almost speechless by the introduction, but let me try anyways. So, first, very briefly, I want to thank all the organizations who has made my work possible, which are listed there, and all my collaborators, which I will not list. Also, my postdoc students and group members. Everyone is of enormous help in my work, which is extremely multi-sided, and I'm learning from everyone all the time, and couldn't do it just by myself. I want to tell you some aspects of my work, and it's somehow centered around certain areas of mathematical physics, which probably doesn't say much to people because it's such a wide scope of topics. So I put some keywords in the title, which is symmetries, probabilities, and mathematical physics. And I'll try to center my talk around these words in a slightly philosophical sense, because in my view, mathematics is not only a science, it's actually part of philosophy. And there's a lot in the thinking process behind all these theorems that we prove. And if I would just show you some theorem statements from the latest papers, wouldn't be much of use to see what's underlying in there and what is the motivation. So I'm also starting with a very quick slide of history, just to motivate something from myself. So I'm interested in mathematics, physics, sciences in general, and I would call myself a little bit as a philosopher. And I wanted to highlight from the year 1900 in the International Congress of Mathematicians in Paris, David Hilbert, who was a mathematician arguably, but also had a very wide range of interests. So he was listing lots of problems in mathematics, and one of them was to provide mathematical foundations to physics, which sounds like impossible tasks, of course. And for some parts of it, progress has been made, and also my own work is centering around these questions motivated by models of theoretical physics, in particular of development of theory of probability to statistical physics models, and also pertaining to quantum field theory and some kind of theories of gravity and so on. And I'm mostly working on two-dimensional models. So here you see some pictures of two-dimensional, very simple models that I also have been working with. So in the left picture, the yellow and purple hexagons represent the model of critical percolation, which is a model of porous material. So you can think about some chunk of, I don't know, of a rock that has a lot of kind of tiny holes in it, and you could ask how much of there in that body is a hole and how much is actually the material. And on the right-hand side is a simulation of the critical easing model, which is a model of magnetic material. And the two colors there represent two types of spins, which is about magnetization, somehow North Pole and South Pole in very simple terms. And in my work, I'm very interested in geometric properties of these kind of models. And people refer to this kind of area sometimes random geometry. And what is very common to these models is that there's lots and lots of objects. So you saw already on those pictures, actually there was some kind of number of hexagons or rectangles colored in the two colors in some random manner that is presented in the model. But then it's impossible to just investigate one particular object, one particular hexagon or square or atom in these models. So you make up statistical models for them, and you study features stochastically, so using probability theory. For instance, in this picture, you see some kind of red interfaces, I hope, some kind of paths in this spanning tree model, and you can ask about those paths coming together in the boundary. So maybe you can see some chunk of them close by if you look at the left side of this rectangle. So you can ask for probability of such events to happen in the model. And in applications, it might, for example, be about if a liquid can pass through this material, or if there's some magnetization in certain places of the material, and so on. And another aspect, so these are microscopic features which you have probabilistic models to understand. There's another aspect which is quantum field theory and somehow the structure of the universe. And in my work, it features as some kind of theory of random surfaces. And I didn't have a nice picture about that, but in the bottom you see some kind of curved shapes that you can glue together and try to form models of surfaces. And again, you can do it in a random manner, and you arrive to random geometry. So how to analyze these models then? So you have an enormous amount of objects there. It's impossible to look precisely, what's happening in each given place. So you try to find some properties on average, some kind of statistical properties, but also you can try to find some symmetries. So you could think about if your system has, say, symmetry under rotation, you already know some things about how the shapes behave, right? Or there's more sophisticated symmetries, like some kind of stretching, or even more fancily conformal symmetry in the two-dimensional models, which is somehow locally preserving angles, sending little circles to little circles, but in the global scale, it can distort the model quite a lot. So in the top, you see this kind of stretching map that actually is the same configuration in both of these top pictures, but the other one has been stretched. So you can ask, how does this kind of transformation change your model? And if you know how it does, you can analyze it using these symmetries. And mathematically, we use algebra, representation theory, and some other abstract methods to actually make sense of these things. Okay. And I wanted to put one box about more close to my own interests. So this conformal symmetry that I mentioned, so you can think about it as some kind of quite rigid transformation of your system. And there are some conjectures that certain models satisfy this symmetry, and that gives them enormous structure that actually gives you tools to prove theorems about those models, prove formulas, for instance, this kind of crossing probability that you see in the picture, that certain colors cross your material in a certain way. But to the majority, this is still only a conjectural level, so physicists believe this kind of symmetry holds for these models. There are a few mathematically rigorous arguments for this, but it's a big area of research to try to understand this conformal symmetry mathematically. So it's something that my own research focuses very much on. So on the one side, finding the symmetry, on the other side, using it. And then there's a small caveat. So I wrote fancy words here, conformal field theory. So what does it mean? It means that these discrete models, whose pictures you've been seeing in the talk, so they should somehow approximate if you take finer and finer grids. So the grid size somehow goes to 0. So from the left to the right, you see that the number of these particles has increased a lot, right? So if you take some kind of limit, you have infinitely many of these atoms, and you should actually arrive in some kind of theory that physicists call conformal field theory, which is a quantum field theory with this conformal symmetry. And that is a mathematically ill-defined thing, because somehow you cannot define uncountably many things at once. So this is a big problem for us to make sense of it. And this slide is supposed to represent this limiting procedure is one way to approach it. So you look at these discrete systems that you can describe in these pictures, and you can try to ask what happens in the limit. Okay, so I want to be a little bit more concrete. So I prepared an example for you. I think I still have time for that. It's very, very simple. So simplest that I could find. And so I've actually worked on a slightly more complicated modification of this problem. So we can actually work on simple things, and it can be quite hard mathematically. So let's look at this model of the hexagons with two colors. So we have some kind of material and holes. And we chuck them together in the configuration, and both colors are equally likely. You can flip a fair coin for each chunk, and you put them together in your system. So you get some kind of configuration. So if you keep flipping the coin independently of the others, you, for instance, might get this kind of configuration. It's quite small, but you could actually do it by hand. And now, because I flipped coins for each hexagon, this is a random configuration. So of course I could generate another random configuration by repeating this coin flipping, right? And then I can ask various questions about what I get in these random configurations. And one is this kind of crossing probability question. So in the figure there is highlighted on the right side of the triangle, there's a piece of boundary which is called A. And in the bottom, there's a smaller piece, which is called B. So they are red. I don't know if you can see them very well. But the idea is that I'm asking if there's a path between A and B via these yellow hexagons. So I'm imagining maybe the yellow hexagons are holes. So if I put some liquid from A, I can ask if it will make it through to B. And what's the probability of this? Okay. So of course, in this picture, you can just calculate it if you want. But now, if you start doing bigger and bigger pictures, it starts to be harder and harder. And first you need to find some kind of means to understand how to discover this kind of passage. And we talk about interfaces, which is just boundaries between the two colors. So you don't need to know very much about them, but they're also random because each configuration is random. So here you see two random configurations, and one of them has this yellow crossing, and the other one doesn't. And you can find it by starting from this segment B, which is in the bottom. Start walking, try to follow the interface between the yellow and purple, and try to see if you can end up in A. So then we end up studying these kind of random curves. Okay, and once your approximation of your actual system becomes better and better, meaning you have more and more of these hexagons, it becomes quite hard to find whether there's a crossing or not, don't you think? And even to define this kind of model, so as long as I have finitely many hexagons, I can say I just flip a coin and color them, right? But now I was interested in this limit, where there's actually infinitely many hexagons, and then I cannot flip a coin anymore for each of them, right? So I need some kind of quantum field theory description of this model, and that's something that we are also trying to investigate from various perspectives. But to the original question, actually symmetry provides a nice answer. So here is the answer. The answer of the probability of the crossing, if you look at it in a very large system, it's approximately just the length of this segment B. So I don't know if you could have figured it out from the symmetry of this rectangle, but it was part of a paper of actually Stas Smirnov, who was already mentioned in almost 23 years ago, something like that. So he proved this, and he also proved much more, of course. But this was one of the most difficult problems at the time, believe it or not. And moreover, this includes something that you can change this shape. So we have these triangles, because it was easy for me to produce also. But I could send it to some other shape, and I know precisely how this probability changes. So this is the conformal symmetry that I kind of mentioned to you, but I didn't want to put it to the slide. The upshot is that the symmetry is somehow very much present here. It's almost miraculous. However, I want to end with an open problem for you. So suppose instead of hexagons, we take squares and do the same game and ask a similar question. So you decide your A and B in some suitable way. So no one has been able to prove a formula for this crossing probability. So we would expect it to be the same. Okay? And you would imagine these squares are equally symmetric as triangles, right? But somehow the triangle and the symmetry there with the triangles and hexagons is so strong that one can prove this result there, but not for the squares. It's not something I'm actively working on, but I wanted to present it as just an illustration of very simply posed questions that are really hard for mathematicians to solve. So thereby I would like to thank and leave the stage.